Microcracking and crazing are among the most insidious failures in automotive coatings because they develop below the visibility threshold and often go unnoticed until secondary effects, such as gloss loss, dirt pickup, or chemical ingress, appear. From an OEM durability perspective, these are not cosmetic defects. They are early warning signs of stress accumulation, polymer degradation, and interface instability that can eventually compromise the protective and aesthetic functions of the coating system. Microcracks are extremely small fractures in the polymer network, often on the scale of microns, that do not immediately penetrate through the full film thickness. Crazing refers to a network of interconnected microcracks that may appear faintly as subtle hazing or shimmer under oblique lighting. Both phenomena are stress-driven and influenced by a combination of mechanical, thermal, and chemical factors. Residual stress from curing is a primary contributor. Every coating layer shrinks during polymerization, and this shrinkage generates tensile stress, particularly in high crosslink density clear coats. If the substrate is rigid, and if adjacent layers have mismatched modulus or flexibility, these stresses cannot relax and initiate microscopic fractures. Undercured layers have lower modulus but higher solvent retention, which can also cause localized swelling during aging, creating microstrain that manifests as microcracks. Thermal cycling accelerates microcracking. Repeated expansion and contraction of a substrate, combined with differential movement between primer, base coat, and clear coat, impose alternating tensile and compressive stresses. Over time, even coatings that appeared flawless at delivery begin to show subsurface network fractures. OEMs validate coatings with extensive hot-cold cycling, combined with humidity exposure, to simulate years of real-world conditions in accelerated lab testing. Environmental exposure compounds the problem. UV radiation embrittles polymer chains, reducing their elongation capacity and increasing susceptibility to microfracture. Moisture ingress through microvoids or edge defects can further swell the polymer, increasing localized stress. Pollutants and acids from rainfall or industrial fallout chemically weaken the network, making microcracks more likely to propagate. This is why panels exposed horizontally, such as hoods and roofs, often develop early microcrazing. Additives influence both formation and propagation. Stress relief additives, elastomeric modifiers, and internal plasticizers can increase the coating's ability to absorb strain without cracking. However, overuse may reduce hardness or chemical resistance, creating trade-offs that OEM formulators must carefully balance. Slip and flow additives can also impact microcrack susceptibility by affecting polymer orientation during cure. Migration of these additives to the surface may protect early-stage crazing, but cannot prevent bulk degradation. Cure balance is critical. Undercured coatings retain residual solvent and unreacted functional groups, which act as plasticizers initially but are prone to oxidation and embrittlement over time. Overcured coatings start brittle and develop cracks early. OEM bake profiles are validated for optimal cross-linking that maximizes both chemical resistance and mechanical flexibility, allowing coatings to survive thousands of thermal cycles before microcracking initiates. Substrate and layer interactions are equally important. Aluminum and steel expand at different rates, and multilayer systems with inconsistent primer thickness or poor intercoat adhesion experience uneven stress distribution. Cracks often initiate at geometric discontinuities, edges, hem flanges, panel joins, before propagating across larger areas. Engineers analyze microcrack patterns to distinguish between substrate-driven stress, intercoat adhesion failure, and intrinsic polymer degradation. Detection of microcracking and crazing requires specialized equipment. Optical microscopy under oblique light, scanning electron microscopy, and dye-penetrant tests are used to visualize subsurface networks that are invisible to the naked eye. Gloss mapping and DOI measurements can indicate early-stage crazing because surface roughness and light scattering increase subtly before visible cracks appear. From a troubleshooting perspective, complaints about early gloss loss, dirt accumulation, or water ingress often trace back to microcracking. Solutions at the plant level are limited. Adjustments in bake profile, film build, and additive balance are more effective. Formulation changes are considered only after systemic causes are ruled out because improper adjustments may introduce new defects. Microcracking is not a sign of poor appearance initially, but a predictive metric for future failures. When coatings are designed with proper crosslink density, additive strategy, curing, and layer compatibility, microcracking is delayed for the intended service life. When ignored, these subvisual failures evolve into visible crazing, gloss degradation, chemical ingress, and premature aging. If you have questions about microcracking, early gloss loss, or subsurface network defects, leave them in the comments. We'll continue exploring long-term durability and aging-induced failures with OEM-level analysis in the upcoming episodes.